All right, so we're going to be looking at special right triangles here. Specifically, we're talking about a 45, 45, 90 degree triangle. In other words, two of the angles are 45 degrees, and then we have a right angle. Then the other one we're going to look at is a 30 degree, 60 degree, 90 degree triangle. And that, in other words, it also has a right angle. Now, in this case, we're talking about the right isosceles triangle. Now, we can kind of think of that in terms of if I take a square, we know that all the side lengths of a square are the same, and all the angles are the same, specifically the right angles 90 degrees. If I draw a diagonal that bisects this angle, then in other words, I'm bisecting a 90-degree angle. Both of those angles should be the same, correct? Well, what's half of 90 degrees? 45. So that's what they're talking about here is if I draw my diagonal here that bisects this angle, I'd have a 45 degree angle here, a 45 degree angle here, and then the same thing on this other side. Now, what's special about the type of triangle that we formed here? In this case, the same triangle, okay? What is special about these two types of triangles that we form with this diagonal? Well, notice this side length and this side length are the same. Okay, in other words, we have two sides that are the same, and the base angles are the same. Okay, that's an isosceles triangle. Specifically, in this case, it's a right isosceles triangle because one of the angles is 90 degrees. Same thing here, this side length and this side length are the same. Both of the base angles are the same, they're 45 degrees, and we have a 90-degree angle. Okay, so this is our 45, 45, 90 degree triangle. Now, what we want to discover is the relationship between the sides. And the way we can do that is looking at these examples here, where they give us the leg lengths of this triangle. In other words, we have 10 centimeters for this leg, 10 centimeters for this leg, but we don't know what the hypotenuse is. They just label it as x. Now, we know if this is a right triangle, we can apply the Pythagorean theorem, our a squared plus b squared equals c squared, and find the missing side x, okay? So if I let this be a, b, and c, then substituting that into our formula here, and again, they show the work here, but I'm going to talk you through the steps. We would have a squared, which is 10, b squared, which is also 10, is equal to c squared, in this case, which is x. So we have 10 squared plus 10 squared equals x squared. Well, what's 10 squared? 100. So you'd have 100 plus 100 equals x squared. Adding that together, 100 and 100 make 200, and we get 200 equals x squared. What's the opposite of squaring something so we can get x by itself? A square root, right? So if I square root both sides, my opposite operations would cancel out, and I get the square root of 200 equals x. Now, they break that apart into two different square roots, the square root of 100 and the square root of 2. Okay, 100 times 2 gets you to 200. And then the square root of 100 would be 10, so we'd have 10 times the square root of 2. In the last video, we talked about simplifying using our factor tree. We would get the same result. For instance, if I take 200 here, and I break that apart, we could say 100 times 2 gets me to 200, 10 times 10 gets me to 100, and then 2 times 5 gets me to 10, and 2 times 5 gets me to 10. So my 2's and my 5's would be my primes. Remember, we're looking for pairs. I have a pair of 2's, a pair of 5's, and one single 2, okay? One single 2. My pairs go in front, so I'd have 2 times 5 in front of the square root, and my singles go on the inside of the square root, okay? Well, what's 2 times 5? 10. So we'd have 10 square root of 2. So we get the same answer as they have, the same answer as they have here, okay? So the side length x there would be 10 square root of 2. Let's see if another pattern emerges here in these next two examples. We have a right isosceles triangle, 45, 45, 90. This side and this side are 2 centimeters. We could call this A, B, and C and plug it into our Pythagorean theorem. So we have a squared plus b squared equals c squared. A squared being 2 squared, b squared being 2 squared equals x squared. Well, what's 2 squared? 4. So we have 4 plus 4 equals x squared. What's 4 plus 4? 8. Then, how do I get rid of a square? Square root both sides, and we get the square root of 8 equals x. Okay, so we get the square root of 8 equals x. Now again, they break it apart here into the square root of 4 times the square root of 2. Again, same idea as if we take our factor tree here, if we break this apart, okay, 4 times 2 gets me to 8, and then 4 can still be broken down into 2 and 2. Well, I have a pair of 2's, that's going to go in front, and then I have one single, which is going to go on the inside. So we still get the same answer, okay? Now, in this example, the reason I wanted to look at this one too is notice the side lengths are a square root. So we have a radical here, okay? So we're dealing with a side length that has a square root. In this case, my a would be the square root of 14, and my b would be the square root of 14, and x would be c, okay? So plugging those in, we'd have the square root of 14 squared plus the square root of 14 squared equals x squared. Well, a square root and a square, aren't those guys opposites? Yeah. So this cancels out, and I'm left with 14 plus 14 equals x squared. What's 14 plus 14? 28. So we get 28 equals x squared. Square root both sides, and I get the square root of 28 equals x. Now again, they break this apart, and you can go through that process too. If you want to use our factor tree, we could break this apart kind of like they do with 14 and 2. And then 7 and 2. So this would give me my primes, right? Well, notice we have a pair of 2's, and then we have one single 7, okay? So I'd have 2 square root of 7, okay? But I do want to point something out to you. They broke it apart as the square root of 14 times the square root of 2, okay? That's going to be important here later on, okay? So we do get the same answer as them, but I want you to notice this because this is going to play a role in our pattern here, okay? So notice, in the first answer, it was 10 square root of 2. Well, what were the side lengths that we began with? 10, right? So we had 10 and 10, and this guy was 10 square root of 2. On this example, our answer was 2 square root of 2. Well, what were our side lengths? 2 and 2, and we ended up with 2 square root of 2, okay? In this example, our side lengths were square root of 14 and square root of 14, and we ended up with 2 square root of 2. But let's backtrack here. This is also an equivalent statement right here, okay? This is also an equivalent statement. Even though it's not simplified, technically C would also be the square root of 14 times the square root of 2, okay? Which would get us to 2 square root of 7. Well, what pattern emerges there? Well, notice it just takes the side lengths, the legs that we began with, and multiply by what? Square root of 2. 10 square root of 2. 2 square root of 2. 14 times the square root of 2, which, if we simplified it, would get us to here. But the principle still remains. It's the side lengths, our A and B there, multiplied by the square root of 2, okay? And that's what this says here, okay? Whatever x is, this guy is just x times the square root of 2. But that's only for a 45, 45, 90 triangle, okay? For instance, let's look at one example here. Let's go down to number 1, okay? If they tell you that we have a 45-degree angle here and a 45-degree angle here, are the base angles the same? Yes. So this has to be an isosceles triangle, and this side have to have the same length. Well, if they have the same length, what does that mean about x? Well, x has to be 5, right? If they're the same length, then this side and this side have the same length. How would I find y? Well, notice, okay, if this is 45, 45, 90, we said the rule is if these two sides are my same sides, then my third side, the hypotenuse, is just this measure times the square root of 2. So if my two side lengths are 5, then y here would just be 5 times the square root of 2. And that would be our answer, okay? Now, also be careful here. Sometimes you have to work backwards. So, for example, in number 4 here, this is a 45, 45, 90-degree right triangle. In other words, it's also an isosceles right triangle, okay? But in this case, it's almost like you have to think about it in terms of working backwards, okay? So remember, this side and this side should be the same, but this side should be x square root of 2, right? Well, do you see a square root of 2 and 30 here? No. So actually, if we want to work backwards here, we can think about it like this, okay? this side length and this side length, if this is 45, 45, 90, aren't x and y just going to be the same thing? Yeah, because these two side lengths are the same, right? So in other words, I don't even really need to worry about y, so to speak. These are both really just x. So let's work backwards here. This guy is supposed to be x squared 2. But what is this whole side length equal to? What is its measure? 30. So think about it like this. We want to know what x is, right? Well, if I divide this side by the square root of 2, does that get x by itself? Yeah. So in reality, we're really working backwards here. Instead of multiplying by the square root of 2, to work backwards, we have to divide by the square root of 2. So these side lengths over here would be 30 divided by the square root of 2. Okay? This side and also this side. However, because we have 30 divided by the square root of 2, we want to do something that's called rationalizing the denominator and make it a simpler form, okay, a nicer form. So what we're going to do is we're going to multiply both the top and the bottom by the square root of 2, okay, and you'll see why here in a second, so that we rationalize the denominator, okay? So we're going to multiply 30 times the square root of 2. Now, if I have the square root of 2 times the square root of 2, anytime you multiply something by itself, isn't that really just squaring it? Well, yeah. Isn't a square and a square root opposites? So if those guys are opposites and they cancel each other out, what am I left with? Just 2, right? So square root of 2 times the square root of 2 is 2. Okay? So now, with this in mind, looking at this example up here, we have 30 times the square root of 2 divided by 2. Well, what's 30 divided by 2? 15. So we end up with 15 square root of 2. Okay, so this side length over here would be 15 square root of 2, and because these two have the same measure, this was originally y, this would also be 15 square root of 2. Okay, so those are some examples with a 45, 45, 90. Now the next triangle that we're concerned with, okay, is the 30, 60, 90 degree angle, or triangle, okay? Now, what that takes is an equilateral or equiangular triangle in which all the measures are 60, okay? And then it draws, okay, we're going to extend this, a perpendicular bisector, okay, that forms the height of these two triangles now. Okay, so when I say a perpendicular bisector that's forming the height of these two triangles, I'm saying I'm splitting this in half. In other words, this segment's length would be equal to this segment's length, but because it's a perpendicular bisector, we'd have a 90-degree angle and a 90-degree angle. Now, if I bisect this angle, which was 60 degrees, what does that make each individual angle? Well, this would be 30 because it's cut in half, and this would be 30, okay? Now, notice, we have two different triangles here, and this line that we extended forms the height of these two separate triangles, okay? That's what we have over here. But what it formed was a 90-degree angle, a 60-degree angle, and a 30-degree angle, okay? Now, just like the 45, 45, 90, this has a special relationship between the sides, okay? Now, notice when we have this example here, okay, let's see if we can find the relationship here between the sides so that we can figure out what x would be. Again, applying the Pythagorean theorem here, we could call this A, B, and C. 8 is my hypotenuse, okay, plugging that in, we'd have 4 squared plus x squared equals 8 squared, okay? Well, what's 4 squared? 16. X squared stays x squared, and 8 squared is 64. Well, then we'd have to subtract 16 from both sides. Subtracting 16 from 64, we get x squared equals 48. Square root both sides. My inverse operations cancel out, and I get x is equal to the square root of 48. Well, again, I can apply my factor tree here and break this apart. They use 16 and 3, so why not? Let's use the same thing. And then we have 3, which is prime. What two numbers go into 16? Well, 4 and 4, whoops, a little bit better 4, and those break apart into 2 and 2, okay? So if I'm looking for pairs again, notice I have a pair of 2s, another pair of 2's. So those guys are going to be multiplied out front. And then my single goes inside the square root. So we get 2 times 2, which is 4 square root of 3. So we get the same answer. Okay? So this side length here would be 4 square root of 3. Okay? Let's try one more. Maybe we don't have to go through all 3 of these to get the idea. Let's try one more. Okay? So in this example here, again, I could call this A, B, and C here. So plugging that in, we'd have 3 squared plus x squared equals 6 squared. Okay? Well, what's 3 squared? 9. Then we have x squared, 6 squared, which is 36. 36 minus 9, subtract that over, and we get 27. So taking the square root of both sides, inverse operation cancels out, and I get x equals square root of 27. Well, again, we can break this apart. We can use the same numbers they do. 9 times 3 gets me to 27. 3 is a prime. And then 9 breaks down into 3 and 3. So now I have all primes. Notice I have a pair of 3's. So we have 3. And what goes on the inside is my single, which is 3. So we get the same answer. So this side length would be 3 square root of 3. Well, notice we already started to form a pattern here, okay? Notice the relationship between the 3 sides. If I let this guy be, let's say, let's pick a different variable than x because we already used x. Let's say it's y, okay? So if 4 is y, how do I get to 8? What would I have to multiply to 4 to get to 8? 2, right? So in a sense, this would be 2y, okay? 8 is double of 4. Now, what's the relationship between 4 and this side? Well, it's just 4 times the square root of 3. So if we think about it in terms of y, this would be y squared root of 3. So whatever this guy is, this guy was times 2, this guy was times the square root of 3. Let's see if that pattern still works here. So if we think of this guy as y, 3, what is 3 times 2 going to get me? 6. So I still have 2y. On this side, I would have y squared root of 3, okay? Well, 3 times the square root of 3, that gets me to here. So that's the pattern that emerges between the 3 sides there for a 30, 60, 90, okay? Now, I used y because they had x listed there, but going back to x here, if the bottom, the shortest side, okay, that's important. The shortest side is x, that leg times 2 would give us our hypotenuse. And the longest leg would be the shortest leg x times the square root of 3. Okay, so understand this. We have our shortest leg, the longest leg, and then the hypotenuse. Okay, so the shortest leg, if we think of it as x, then the longest leg would be x times the square root of 3, and the hypotenuse would be 2 times x, whatever that number happens to be. Okay, so using that then, let's look at this example down here. Okay, maybe number 12. And in that example, they're telling us that our shortest leg, which we can think of as that x value, is 4. Well, the hypotenuse would be 2 times 4. So y over here would be 2 times 4, which is 8. Okay? And our longest leg is our shortest leg times the square root of 3. So it would be 4 times the square root of 3. Does that match the relationship that we saw? Yeah, this was 4. 4 times 2 was 8. And 4 times the square root of 3 gives me that guy. Okay, so that's the relationship between the sides there. Okay, now again, in some examples, you might have to work backwards here and you might have to divide out. For instance, maybe, let's see if we can think of a good example here. Oh, maybe let's look at 19. Okay, so on 19 here, okay, they give us the longest leg instead of the shortest leg, okay? So working backwards here, we know the shortest leg, x, that guy, to get to the longest leg, we'd have to multiply x times the square root of 3, right? So if I want to work backwards, that means I need to take my longest leg and divide by what? Square root of 3. Or another way to think of it is this longest leg should be x squared of 3, so I'd have to divide by square root of 3 to get x by itself. Either way, I need to divide by the square root of 3 to get to the shortest leg. Well, again, we can rationalize the denominator, multiply square root of 3 to the top and the bottom here. So you'd have 12 times the square root of 3. Again, if I multiply a square root by itself, that's going to square it, and inverse operations cancel out, so we just get 3. Well, what's 12 divided by 3? 4. So this guy would be 4 square root of 3. Now, the hypotenuse is double the shortest leg. So what's my shortest leg? 4 square root of 3. So if I double it, it would be 8 square root of 3. Okay? So now I have my sides.